Hello, welcome everybody to the next lecture by Professor Goswami. Today's talk, I think, is going to be very topical. He'll tell you more about it.
Ah,
BNG.
Thank you, Rama. And good evening, everybody, and welcome to this talk. Today, I'm going to talk about the quasi-biennial oscillation. We might ask, why talk about quasi-biennial oscillation? Actually, I'm quite excited about this phenomenon itself, and it is a very exciting atmospheric phenomenon which has relevance to the Indian monsoon. And in the coming years, it appears that at the end of the talk, you will realize that in the coming years, this is a very predictable phenomenon. And apparently, this predictable phenomenon is going to be rather unpredictable in the coming years because of the global warming. And that unpredictability is going to link Indian monsoon and add some unpredictability to the Indian monsoon, I suppose. So therefore, there is relevance in understanding these phenomenon in greater detail. So that is why I am going to talk about it today. So there is a lot of good material about this QBO. There is a book by Andrews, Holton, and Leovy. It has discussed all the basic fundamental theory as well as the observations and the theory about QBO. And it's a very well written, exciting book. And there are, of course, several review articles in reviews of geophysics by Baldwin et al. In 2001, and one of the earliest reviews was by Mike Wallace in 73. So there's a lot of material in this on this. So most of my sort of material is taken from some of these resources. So before going to discuss the actual phenomenon, we have to recognize the background on which it takes place, and that is the climate of the stratosphere. This is a phenomenon in the lower stratosphere, and the climatology of the upper atmosphere in the lower stratosphere is different from the troposphere. And in the troposphere, we know the temperature is kind of symmetric about the equator, but in the stratosphere, the temperature distribution is this we had discussed in the first class, is rather asymmetric, and in the extratropics, and there is a strong semiannual oscillation. And therefore, associated with that, there is asymmetry in the zonal winds as well. And therefore, the climate of these of the upper atmosphere is quite different from that of the troposphere. And this what is happening is in that background. And if you look at the climatology of the winds, which I had shown in the first lecture, is or the second lecture, that this is there is asymmetry in the upper atmosphere, but the climatological mean, the annual mean winds in the equatorial or tropical region is rather weak in the stratosphere also. And in that, the variability, the year-to-year variability in the lower stratosphere of the zonal winds is very high. This high year-to-year variability comes from something known as this. So if you take the annual mean of the zonal winds and do a year-to-year variation or standard deviation of the year-to-year variation, that is pretty high in this region. And where does it come from? It comes from, this is where the something called this biennial oscillation takes place, and that biennial oscillation gives rise to large year-to-year variability on these, and therefore the long-term mean climatology is rather the difference between the positive and negative phases of these oscillations, and that is why it is rather weak. That doesn't mean that the actual winds are weak there. The actual winds are rather strong. And so below 35 kilometers in the stratosphere is dominated by a long oscillation called quasi-biennial oscillation, and that has a period of about 27 months. And this oscillation that oscillation has pretty large amplitude, and I'll show that in a minute. the this period has nothing to do with the solar forcing, because solar forcing doesn't have a 20-month period in that. So where does it come from? So it comes from essentially some internal dynamics of the atmosphere, and that was initially discovered by Reid in 1960, and later on by other people, Varied and Epson, and so on and so forth. And these, once that was discovered, the remarkable regularity was quite stunning, and therefore people quickly tried to understand what produces this kind of remarkable regular oscillation, and that is what we are going to discuss. So if you look at any station like the Singapore, or there are some stations where there are balloon observations which has long records, and then if you look at the CR of the vertical wind between 30 and 50 millibar, and that CR has a very nice regular oscillation of this is amplitude is about plus minus 10 meters per second. And associated with that, there is also temperature of the layer is also changes by about plus minus 4 degrees Kelvin. So this is the kind of large oscillation. The interesting thing is the regularity of this, and this period is about 27 months. It varies from about 25 months to about 30 months, but roughly around on the average about 27 months, which is quite remarkable. Another interesting thing is that these oscillations are rather coherent throughout the equatorial belt. So people realized early on that whether you take measurements in Singapore or in Balboa or some other place which is closer to the equator, somewhere far away, they are all in the same phase. That means that if you do an average of around the equator, 2 degrees south to 2 degrees north of the zonal winds at 20 millibar, and plot it along the longitude and time, then it shows that at any given time, everywhere along the equator, the same phase occurs. So therefore, it is an equatorial phenomenon which is around the globe, and that is also something that gives us some clue about why it possibly happens. So, so there is record of now several stations in this in the equatorial region, and by combining those stations, we can actually produce a long record of this. This particular record is only from Singapore radio sounds. This Singapore has from 1980 onwards a good record, and that record shows that if you plot around the equator, at that station with the vertical and in time, this shows that some of these their westerlies occur at some point of time, and they seem to propagate downward. These westerlies are as large as 25-30 meters per second maximum sometimes, and 30 meters per second. Then it propagates downward. This is tropopause, but it doesn't come down below tropopause. Then at some other easterlies start forming at upper level. Then they also propagate downward. Then again the westerlies start forming at upper level, propagate downward, and this repeats. And this repeats, and this repetition is rather very coherent and very regular, and that is what made it very remarkable. Except when in the recent years there is a couple of abnormality, and this is what is happening recently. In all these years, it's so regular, but suddenly in 2016 and in again 2020, this westerly phase was coming down. Then suddenly an easterly phase started forming. This was supposed to go down, and then easterly was supposed to form here and then propagate down. Instead, a westerly again started. Similar thing happened in this 2020 also, and so this is a disruption. These are called now disruptions. So we'll come back to that towards the end, but this is beginning to happen only in recent years. Now these So, so the characteristics is that these oscillations start the easterly phase or the westerly phase all start at the upper atmosphere around 10 millibar, 5 to 10 millibar, then propagate downwards, and and the westerly phase is always stronger than the easterly phase. The easterly phase amplitude is a little bit smaller than the westerly phase, and the regularity is almost very regular. And and if by putting together more um, mm, so this is again seen from not only from one station, but now if you do reanalysis, the Mira 2 is a new updated reanalysis data. I discussed about the reanalysis and reanalysis in the first talk. And from this data, all the global data has been put together, and then the model produces these biennial oscillation, and you can see the same features and seen the same disruptions during 2016 and 2020 can be seen. More by putting together, because this is uniform across the globe around the equator, then you, by putting together different station data, you can actually produce a record at much longer record, not just the record that is available at Singapore, but if you take other stations, Canton Island and Gan Island and Singapore, and all these three station data, if you put together, then actually you can see this oscillation taking place all the way from 1950 early 50s to the latest period, and it has for 27 odd periods it has remained very regular, except in 2016 and 2020 these disruptions happened. So this is the character of these, and these can be summarized when you look at this amplitude and the phases of this oscillation around the around equator and with height, it turns out that it has a maximum amplitude around 30 millibar. So the amplitude between positive and negative easterly and westerly phases, that amplitude, if you average, it is about 20 millibar, 20 meters per second, and then if you see this, the amplitude decreases away from the equator. So it is an equatorially trapped, equatorial phenomenon. And the amplitude comes down and becomes weaker, and by about the tropopause, it becomes very insignificant. I'm sort of very small, indistinguishable with the other year-to-year variations of winds at that point. So, and these are the phases. The phases are sort of more or less coherent with the latitude, and then they in a month they sort of in about 1, 2, 3, 4, 5, 6 or 7 months from about 10 millibar to about 100 millibar, it comes down in about 7 months. So about so that is the kind of these are every month the phases shown here. So amplitude is largest at the equator at around 30. This is equatorial trapped. Half width is about 12 degrees. Phase propagation is downward and sort of independent independent of latitude. Now, the changes, as you can see, that acceleration, or if you see how it change the positive, the easterly phases propagate, and how the westerly phases propagate is slightly different. And so, when it changes from easterly to westerly, the rate at which it changes from easterly to westerly is different from westerly to easterly. That is what is shown here as the acceleration. So if you take do a sort of lead lag of these phases starting from the center, and as you go, how the from the this is from easterly to so this is around the westerly, and then from easterly to westerly, how it goes, at what rate it goes. So westward and eastward accelerations are asymmetric. The westerly acceleration is stronger than easterly acceleration. Westerly acceleration starts at the equator and spreads to higher latitude, and easterly acceleration starts almost simultaneously at all latitudes. So this is this difference. It starts here and then kind of spreads, but here it starts and sort of spreads all, at all latitudes. So this is the kind of some nitty-gritty. So this is associated with, obviously, as we see, as we go back here. So at any point of time, there is a vertical shear, right? There is this is easterly at the top and westerly at the bottom. So this is a vertical shear is you can call easterly shear. And here, when you come here, westerly at sort of easterly at the bottom and westerly at the top. So this can be in westerly shear. And so this shear also keeps on changing. So there is a vertical shear of the winds, and that vertical shear also changes with this. And these essentially, because of the vertical shear of the wind, the winds are essentially on thermal and this large scale and slow oscillations. The winds are always in thermal imbalance, and therefore associated with the vertical wind shear, there has to be a temperature gradient in the north-south direction, and that therefore there is a implied temperature gradient in the north-south direction. So essentially, when there is westerly at the top and easterly at the behind, there has to be warm conditions in the equatorial regions and colder conditions to the north, and that is essentially due and opposite in the easterly shears, and that is due to these thermal wind relationship. This is essentially an adiabatic process. It is essentially how does it happen? It produces a implied secondary meridional circulation. So this meridional circulation produces upward motion and cooling in this region, and therefore there is a cooling. That cooling and warming here due to warming to, away from the equator, and therefore there is a cold to warm gradient, which is consistent with the easterly at the top and westerly at the bottom. Similarly, here there will be an opposite meridional circulation, which will produce downward motion here and warming, adiabatic warming, and upward motion here, adiabatic cooling. So this warming and cooling is again consistent with this vertical. So associated with this here, there is an implied this is north-south anomalous circulation, meridional circulation. So this periodicity, you can see that is almost sort of nearly periodic. It doesn't change very much, and you can represent this by doing an UF of the winds as in the vertical direction from 10 millibar to 100 hectopascal. The UFN 1-2 represents a periodic oscillation, the largest variance and periodic oscillation. And if you plot that in the principal components of these two UFs, and it sort of goes round and round as is expected in an oscillatory character. But except during these the 2020 and 2016, that disruption shows that this changed the periodicity. In fact, this why change the periodicity? If you go back into these, so it appears that these disruptions appear like because the easterly phases should have come down like that. Now the westerly phases come again. So therefore, the periodicity seems to have decreased. Sort of this this makes the periodicity somewhat shorter locally in this through this disruption. So that is exactly what you see here, and that is what we may be expecting in the coming years due to more disruptions if it happens. And some model studies indicated that with the global warming, there could be more disruptions, and therefore the periodicity can also change, is likely to change. So let us talk about then the theory of this. So how do we understand this? So we have to, a theory of QBO I must explain. It's quasi-biennial periodicity and occurrence of regionally symmetric westerlies at the equator and downward phase propagation, asymmetric phase propagation of westerly and easterlies. So, so essentially, this is always the attempts to explain QBOs due to adiabatic heating due to lateral exchange of momentum were unsuccessful in explaining these features. A model of QBO based on vertically propagating waves originally proposed by Lingen and Negram and later on Holton and Lingen actually could predict sort of predict almost all the features of this, and that is essentially the basic theory of let me try to explain that in a minute. So essentially it was recognized by the meteorologists that when the waves propagate from troposphere, the equatorial waves, whether it is inertial gravity waves, the Kelvin waves, mixed Rossby gravity waves, or Rossby waves, they can propagate vertically up. And when they propagate vertically up, they have to go through these wind shears. Suppose there is the wind shears in the upper atmosphere. When they go through the wind shear, at some point of time, they can get their phase group velocity may come to zero because of the Doppler shifting. And at some point of time, and then they can possibly interact with the mean flow at that point, and they modify the mean flow by that process. So this was sort of conceptually sort of plausible hypothesis, and already we knew that the gravity waves do propagate up, but the gravity waves, and then they deposit energy in the upper atmosphere, mesosphere, and the higher stratosphere and mesosphere. And that happens due to non-linearity, because then the gravity waves become non-linear, they break. But even if they are not non-linear, the waves can produce interaction between the mean flow and the if their group velocity becomes stationary or zero. And in that case, then they will spend a lot of time in that certain region, and through dissipation, then they can exchange energy to the mean flow, and therefore, so if it happens, then there is a potential for having the wave in mean flow interaction, and that was the basic premise. With that, you need to integrate two things. One is vertically propagating gravity, vertically propagating equatorial wave. I discussed the horizontal propagation of the waves, but we did not discuss. So let me go through quickly the vertically propagation of the same things, and then we need to understand how the waves and their fluxes could influence the mean flow. So how the wave and mean flow interact. So there are two elements of this theory. One, we have to understand first how the waves propagate and what will happen to their phase velocity in the vertical direction, as well as the group velocity in the vertical direction, and how that phase and group velocity are affected by the mean flow. So that is something that we need to understand. Secondly, we need to understand is, okay, now I have this wave. The waves can produce energy flux, like we did in the Rossby waves in the extratropics, produces transports, and there's transport convergence of the wave transport or wave fluxes give rise to momentum fluxes, give rise to changes in the mean, and heat fluxes give rise to vertical velocity changes, and these essentially produces mean flow changes. So similar thing can happen here through the vertically propagating waves in the tropics, and that let us see how it can. So this is, I will rather go quickly, just mention the important points that now we have to talk about. We cannot use the Shellwater equations because now we have to use the stratified equations. So these are linearized stratified equations where this is again the continuity equation, but now the density is not fixed, so therefore this is dependent, and then there is a in the temperature equation we have this Brand-Weissel frequency. So Brand-Weissel frequency depends on the stability. This theta z is the vertical gradient of the mean temperature, and of course there is a scale height, scale height as the atmosphere density temperature density decreases exponentially, and that has introduces a scale height problem here. So this is the vertical variation of the Brand-Weissel frequency, which depends on basically the stability. So with that, we can do again look for wave solutions, and the wave solutions will always must have a vertical structure like this, and with that we can from this equation I can get a vertical velocity, and then from the other three equations I can get a horizontal structure functions. Now these de facto m square by 1 is rather just let me is in getting equation 8, we have replaced the factor m square by plus 1/4 h square by m square. This is justified for many equatorial waves for which the wavelength is less than, vertical wavelength is less than 15 kilometer, and for that this term is essentially is larger than 34, and that essentially allows us to make this approximation. So with some of these approximations we can find the solutions. Find the vertical, so you can find the find the relationship between the wave frequency in the horizontal direction, and this is kind of a frequency sort of vertical wave number, and see phase speed in the vertical is given by this n by m, and the group velocity is now proportional to I'm sorry, this is the phase speed in the horizontal direction, but no. No. This is phase speed in the vertical direction. So the group speed in the vertical direction is proportional to this, and now in the absence of mean flow, this group speed is just proportional to 1/omega square by n into k. But now suppose there is a mean flow. If there is a mean flow with vertical shear, then it is difficult to resolve these equations very easily. But if we can make a simple that the mean flow is rather weak, the shear is rather weak, then you can do some WKBJ approximation, and then can show that your frequency will be modified locally as omega minus ku, just like a Doppler shifting, and then you have the vertical, then the vertical group velocity, the energy propagation in the vertical will be something like this, where it is omega minus kuz divided by nk. This is very important, which means that the the wave has a particular this omega is of course the horizontal wave frequency that associated with the horizontal propagation of the waves. So the omega by k is the phase speed in the horizontal direction, and that phase speed, for example, Kelvin waves or Raspberry gravity waves, has a particular phase speed, and that phase speed is when that phase speed is equal to the ambient mean flow, then the group velocity will become nearly zero. And that is the important conclusion from all this. So when the phase speed omega by k is equal to uz, the vertical wavelength is nearly zero, and then the group velocity is nearly zero. So then the wave will spend a whole lot of time in that space, wherever that happens, whenever that happens. Therefore, then the dissipation can act on it, and therefore then dissipate the momentum associated with it, and that momentum then can change the mean flow. So same thing can be done for the mixed Rosby gravity. Oh, by the way, this exercise was for the Kelvin wave. So I can do the same thing for the mixed Rosby gravity wave. If I do that, mixed Rosby gravity wave, the group velocity in the vertical is proportional to, again, similarly, omega by k minus uz to the power 3. So that is also, again, same thing, that whenever the phase velocity of the wave is equal to the ambient mean flow, then the group velocity will go to zero, even for the spread propagating Gosby gravity waves. So these waves can then become stationary, or the wave packet can remain in that place for a long time. So and then the dissipation can dissipate their momentum to the background. So that is how it is likely to happen. So we recall that the Kelvin wave has its own structure. V is equal to 0, U and phi are symmetric about the equator, and their this is we are talking just now. We are talking right at equator. Therefore, these are values at the equator, and mixed Raspberry gravity wave is asymmetric about equator. Therefore, the U and phi are asymmetric. V is symmetric. So that that structure we have to keep in mind. So now let us go back to how the waves can interact with the mean flow. So if there is a lot of theory, actually, I'm not going into great details of this, but if you look at it, you solve the equation for the time mean, then there will be it decomposes into the time mean plus the perturbations, deviations from the time mean, which are the eddies, let us say. Those eddies are prime quantities, and so the time the time variation of the mean is essentially driven by the divergence of the eddy fluxes and dissipation. That is what roughly we saw in that in the large scale eddy transports that I had discussed in the first or second lecture. So so this is basically, and where this is what is known as the Eliason pump fluxes, where these this comes from the different waves, and then the different waves, and nu is the viscosity. So I'll discuss this in a little more detail. So these fluxes are essentially, here we are talking about vertical fluxes. But zonal momentum fluxes in the, so the vertical fluctuations of the winds are transporting zonal momentum. So that U prime or W prime U prime is the zonal momentum flux transported by the eddies in the vertical direction. And if there is a net flux like that, that can influence this. And if that has convergence and divergences at some level, that convergence and divergence of the vertical momentum flux can influence the mean. And that is how, and this we can calculate by knowing the structure of these we can calculate these. And that is so these, of course, the people knew that there are Kelvin way back in early 70s. The Wallace and Kursky discovered that there is a Kelvin wave, and there is mixed transmissibility wave, and there are characteristics of different phase speed, length scale, and so on and so forth. The time scale, 15 days and 4 to 5 days, and so on. Later on, of course, as I showed you, with more data, we can now see that not only those waves, there are other waves also. Those particular waves, there is a spectrum of mixed rosby gravity waves possible, and there is a spectrum of Kelvin waves possible, and these all can influence the mean flow, mean flow in some ways, and maybe more than one of them can influence it. So there is a spectrum of these waves. So then there is based on these, people developed something, a very simple two-dimensional analog model for cave. Now this analog model assumes that, let us forget about the differences between the Kelvin wave phase speed and the Rossby waves. Assume that there are just two inertia gravity waves, like inertia gravity, so one eastward propagating and westward propagating. So consider a pair of inertia pair of eastward propagating and westward propagating waves, and this kind of a waves is two traveling waves in the opposite direction is like a stationary wave. Suppose there is a kind of a stationary waves in the tropics, which is produced by one eastward propagating and westward propagating. They can produce vertical propagation of these two different waves, and that vertical propagation can influence the mean flow in the following way. The way it can do is the following. Suppose you start with an initial mean shear, a mild mean shear, westerly shear, which has gone. Now the Kelvin type, the eastward propagating wave, will have positive phase velocity. This phase velocity means they will get absorbed in where their positive phase velocity is equal to the mean flow. So that has to be westerly mean flow. So they will get absorbed in some westerly mean flow somewhere here. And on the other hand, these the westward propagating wave, like mixed Rossby gravity wave, cannot get absorbed here, because they will propagate, their phase velocity and mean flow will not match, and therefore they will propagate up somewhere up in the above. There will be an easterly flow, and that easterly flow they will then get absorbed, and then they will deposit their energy. Now what will happen when they deposit their energy in that then the maximum of this westerly this energy, this carries westerly momentum. This westerly momentum adds to this westerly mean flow, and therefore makes the maximum lower higher at a lower height. So therefore, the height of the sort of maximum of the mean z will come down, and when it comes down, it will then this wave will get absorbed at an even lower height, and that height will again add more momentum and then bring this mean down, and then the wave will get absorbed at a lower and lower height, and then these waves are getting produced at the troposphere, and they are propagating all the time. So these more and more waves are coming, and they're getting absorbed at a lower height, putting energy into the mean flow, and that mean flow is going down. So the westerly winds here will increase, and their maximum will propagate downward like this, and this one will then do the other way around. From the top, it will start getting absorbed in some easterly flow, and that easterly maximum will come down. Then this wave will get absorbed at a lower height, then the easterly maximum will come down further, and then it will absorb in a lower height, and it will go on and on like that. Then the easterly phase will also start propagating downward. So that is a possibility. And then how does the vertical shear changes, or sort of vertical shear of the mean flow changes sign? Then of course when it comes down too low, the easterly shear, and also you have the westerly shear, then the shear between the westerly and these becomes very high. Now, when it becomes very high, then the dissipation will break it down. Then the dissipation, this will produce turbulence, and the turbulent dissipation will then kill this shear and make this an easterly flow at the bottom, and the westerly at the top. So like this, so it will make the easterly at the bottom, and sort of easterly flow very high up. Now these the easterly waves will further try to bring it down, and now this one will propagate much further up, and then at the upper height where there is an westerly, then it will start producing, getting absorbed there, and then try to bring that westerly down, and further it will bring it down, and then it will become this westerly shear and easterly shear D will become very high at some point of time, and then the turbulence again will bring sort of kill that shear, and therefore will make it a westerly shear at the bottom, westerly winds at the bottom again. So this is a kind of conceptual model that you can think about. And this actually was demonstrated in a laboratory by Plum and McQueen. They developed a concentric cylinder in which they put salt water and a membrane at the bottom. This salt water produced the stratification, essentially. That is what is required. Stratification is important. A stratified fluid is required. And so then you have this membrane. Membrane was divided into a large number of sections so that you can produce vibrations and produce a stationary wave. So by using some properly tuning fork in a way that you can produce a stationary wave. Once the stationary wave is produced, the annular vessel is filled with salt stratified water and a flexible membrane divided into a number of equal segments. The membrane oscillated to produce the standing wave forcing and excited two vertically propagating internal gravity waves and equal and opposite horizontal speed. So dissipation was by viscosity. For forcing above a critical value generated, a strong inflow consisting of downward propagating alternating westerly and easterly regimes were seen very nicely. So this is something like what is, and this was experimental provided evidence that Halton and Lingen mechanism. Now, Halton and Lingen mechanism I have not discussed. Let me discuss that Halton and Lingen mechanism here. So what Halton and Lingen did is used the same theory. Now, instead of using two gravity kind of waves it's propagating in the opposite directions and stationary waves, they actually used the structure of these Kelvin and mixed Rossby gravity waves and produce this Eliasson pump flux calculated. And of course, they added the dissipation is similar. They added the semiannual component, which is semiannual forcing, which is actually of the realistic atmosphere in the upper atmosphere has a semiannual cycle. So you need to put that in as a background. So with that they calculated and they use a certain Newtonian cooling coefficients and some reasonable numbers for that. The phase speed of the Kelvin, phase speed of both the waves were considered equal. Wave number, yeah.
In the previous slide, and in some other slides, you've been using this U bar and also saying it's a function of time. Could you explain what
No, not function of function of time. It is a sort of slowly varying function of time because mean it's averaged over this. The time is averaged over a monthly mean. So monthly mean or monthly or 3 month mean. So the monthly mean values have to be Yeah, you are right. Yes, I'm sorry about that. But these the waves are of shorter durations, right? If, 3 to 5 days
Okay.
or 10 days, right? So these are means of the, but these means itself can have temporal variations on a longer time scale. So these means are essentially a seasonal mean, 3-month mean.
Okay.
So basically we are looking at, suppose we are talking about 3-month mean, how that 3-month mean can change over a longer period of time. And that is, I think, the basic philosophy about this. Yeah. Um, um, is that okay?
Yeah, yeah, thank you.
Okay, okay. Um, okay, so okay, with that they could actually put that into the, and with some few reasonable numbers of these, they could put and integrate that equation and actually find so that these oscillates just like what we expected in that conceptual model. So both easterly and westerly phases start at a higher altitude, propagate downward, and repeats with a periodicity of roughly about 2 years. Uh, roughly about 2.5 years. So, but they had a problem. One major drawback was that the easterly shear zone was much stronger than the westerly shear zone. The observations showed that westerly shear zone were much stronger than the easterly shear zone. But it turned out that in their case, easterly shear zone is stronger than the westerly shear zone. In the contrary to the observation, we find that the westerly shear zone is a bit stronger than the easterly shear. So but basic concept was quite well demonstrated. So later on, people tried include the variation of the mean variation, meridional variation of the mean wind as the mean temperatures, and then they were able to simulate more or less what is observed. So it is essentially, basic theory is very simple, and it can explain the most of the observed characteristics of the quasi-biennial oscillation through an wave-mean flow interaction of these two the Kelvin waves and in a mixed Goswami waves, particularly propagating up and then affecting the mean flow over there. So that sort of is sort of, it was very intriguing and very simple theory which explained. Then came this sort of unusual observations that were seen in 2016 and 20. So these disruptions became started raising some new questions. Now, what produces these disruptions? So far, essentially, we looked at the vertical momentum flux of the planetary equatorial waves, where the convergence of these vertical momentum flux is what was involved, and we did not think about if you look at a belt in the sort of tropic equatorial belt, there will be vertical momentum flux in that any of the layers in the, but there could be some horizontal momentum flux also, and which we have not considered. Because this, but the momentum flux may be weak, but it turns out that we did not include the horizontal momentum flux like the del u del y of v prime u prime. This also could influence in that equation. Actually, this can add, but it turns out that these people have these disruptions that happened in 2016. People found out that the northern hemisphere was very active in the lower stratosphere, and in the Elias and Planck flux were very active during that period. for whatever reason. So it appears that maybe the horizontal convergence of momentum flux had an important role to play in these disruptions. Again in the 2020, some other studies found that the southern hemispheric elation plumb fluxes were much more active, and therefore the southern hemisphere fluxes had possibly contributed to changing the mean flow in 2020, or in 2016, maybe northern hemispheric fluxes. In addition to the local vertically propagating fluxes, these fluxes seem to have had a different effect, which changed the course of the vertically propagating fluxes affecting the mean flow. And that is why appears to be these disruptions seem to have happened. And so so these disruptions have made one very serious. So this is a very big area of research now going on. People are looking at it of different some papers I have just mentioned. So these disruptions have made that it's a very highly predictable signal that used to be there in these seem to have become rather unpredictable in the recent years. So this is an important consequence and important thing that we need to worry about and understand. And that is so this actually then people have started looking at also what can we expect. Is it due to the global warming? People have started looking at that. Maybe the global warming is changing probably the large scale the circulation changes might affect the elation plumb fluxes in a different way as the global as the earth warms due to the increase in the carbon dioxide. And people looked at it, and they find that indeed the periodicity of the in a sort of twice, 2 times increase of carbon dioxide or 4 times increase of carbon dioxide indeed appears to decrease the periodicity by about 8 to 11 months, and decrease the amplitude of the QBO by 36% to 51% in some studies. So it appears that the global warming could possibly make changes in these significant changes in the period and the amplitude of these, and there are some studies that are also looking at these. The effect of the gravity wave drags. What is global warming? As the globe warms and the tropical convection becomes more and more intense and more intense because the extreme events are going to increase. So therefore, more and more gravity waves activity will increase in the tropics. Therefore, increase in the gravity waves could also have an influence on the vertical flux, and whether or not that will get absorbed in this area or and change in some way, that is a subject of study that is going on, and it's not clear at this point of time. So people looked at also these to see that what will happen in the projections. People looked at now the new CMIP6 models and their projections. It turns out that the models, most of the climate models, did not have a very good stratosphere, highly resolved stratosphere to simulate the QBO correctly. The only recent models have started doing that. The CMIP6 models have started doing that. But in this CMIP6 model also, only about 10 models seem to do a reasonable job of producing this, but it's a variety of variation. Just like in monsoon simulations, in most of the models have a lot of biases. Even the simulations of QBO still have biases, but it is beginning to simulate them reasonably. But it indicates the similar thing, that from the doubling carbon dioxide experiments, whatever people have seen, that it is likely to weaken, the amplitude is likely to weaken, and their period is likely to decrease. And that seems to be something that is also has a signature in from the CMIP6 models. So it turns out that the QBO may be maybe heading towards a sort of uncertain times in the coming years. So QB is basically, in conclusion, what I want to stop today, saying that QB is a very fascinating example of how equatorial waves and mean flow interaction can produce near periodic oscillations of the mean flow in the lower stratosphere. Until and then simplest theory can, a very simple theory can explain the 27 odd uninterrupted QB cycles until it was disrupted in 2016 and then again in 2020. So global warming seems to be increasing the upward gravity wave flux in the tropics, and increasing the variability of the equatorial flux from the extratropics. So that is still a sort of something that needs to be quantified more clearly, and this is where I think some research is going on today now. So with that, I will stop. Thank you.